So I have a vector valued function h here. When I say vector valued, it means you give me a t. It's a function of t. And so you give me a t. I'm not just going to give you a number. I'm going to give you a vector. And as we'll see, you're going to get a two-dimensional vector. You could view this as the x component of the vector and the y component of the vector. And you are probably familiar by now that there's multiple notations for even a two-dimensional vector. For example, you could use what's often viewed as engineering notation here, where the x component is being multiplied by the horizontal unit vector. So you might see something like that, where that's the unit vector plus the y component, 4t to the fourth plus 2t plus 1 is multiplied by the vertical unit vector. So these are both representing the same thing. It just has a different notation. And sometimes you'll see vector valued functions with an arrow on top to make it explicit that this is a vector valued function. Sometimes you'll just hear people say, well, let h be a vector valued function, and they might not write that arrow on top. So now that we have that out of the way, what we're interested in is, well, let's find the first and second derivatives of h with respect to t. So let's take the first derivative, h prime of t. Well, as you'll see, that's actually quite straightforward. You're just going to take the respective components take the derivative of the respective components with respect to t. So the x component with respect to t, if you were to take the derivative, so with respect to t, what are you going to get? Well, we're going to use the power rule right over here. 5 times the negative 1, or times the negative, you're going to get negative 5 times t to the 5 minus 1 power, so t to the fourth power. The derivative with respect to t of negative 6, well, that's just 0. So that's the rate of change of the x component with respect to t. And now we go to the y component. So we're going to do the same thing. Derivative with respect to t is going to be, and once again, we just use the power rule. 4 times 4 is 16t to the third power. Derivative of 2t is just 2. And then derivative of a constant, well, that's 0. We've already seen that. So there you have it. So this is the rate of change of the x component with respect to t. This is the rate of change of the y component with respect to t. And one way to do it, and vectors can represent many, many, many different things, but the type of a two-dimensional vector like this, you could imagine this being h of t being a position vector in 2 dimensions. And then if you're looking at the rate of change of position with respect to time, well, then this would be the velocity vector. And then if we were to take the derivative of this with respect to time, well, we're going to get the acceleration vector. So if we say h prime prime of t, what is that going to be equal to? H prime prime of t? Well, we just apply the power rule again. So 4 times negative 5 is equal to negative 20 t to the 4 minus 1, so t to the third power. And then we have 3 times 16 is 48 t squared, and then the derivative of 2 is just 0. And so there you have it. If you view t as time, for any time, if you view this one as position, this one as velocity, and this is acceleration, this would now give you the position, velocity, and acceleration. But it's important to realize that these vectors could represent anything of a two-dimensional nature.